This tutorial discusses the periodic trend for ionization energy. The ionization energy is the energy required to remove an electron from an atom in the gas phase. The first ionization energy increases across the periodic table from left to right. You'll notice that in this visual, it has very high ionization energies to the upper right hand corner. This is because the Z effective, or the effective nuclear charge, increases due to the poor shielding ability of the p electrons. The first ionization energy also decreases as you go down the column. Due to the increase in atomic size and the decrease of the effective nuclear charge. This is why metals lose electrons more easily than nonmetals and are good reducing agents, because they have the lower first ionization energy. When we're referring to the first ionization energy, the first is referring to the first electron lost. The amount of energy to take to remove the first electron. Nonmetals lose electrons with difficulty, which is why they have really high first ionization energies. So here's the periodic table. Let's take what we just said and put it in more visual, something that you can use on a daily basis. We stated that the ionization energy increases from left to right, and it decreases as you go down. Now, it would make sense then, instead of decreases on the way down, let's make it all apples to apples, and we're going to reverse this and say it increases as you move up. So it increases up and to the right. So it's very similar to the trend we saw with the Z effective and the trend we saw with the atomic radius. Everything kind of locates itself to the upper right hand corner here. So the Z effective was very high here. The radius was the lowest here. And now we're seeing that the ionization energy is the highest. And it all has to do with the attraction between those protons and the electrons. Ionization energy is an endothermic process, meaning that you need to add heat to make it work. So let's compare the amount of energy we have to add. For the first electron that we're removing, so this is the first ionization energy, takes 738 kilojoules. Once we have one electron out, it's going to take even more to get the second one out. That's because there's a greater pull. Remember, there's protons in the middle. There's 12 protons in the middle. Originally, there are 12 electrons on the outside. 2 electrons and then 10 electrons on the next shell. When we take one out, now we still have 12 protons. It gets sucked in because now we only have 9 electrons on the outside. So it's going to take even more energy to take another electron out to make it 8 on the outside. But look how much it jumps to go from 8 electrons on the outside down to 7. That's because this is the 2p2, 2p6 formation. We have an octet on the outside once we remove those 2 electrons. In order to break that octet, it's going to take an awful lot of energy to do so. So the first energy is hard. Second energy is harder. Once we get to the point where we're breaking the full octet, it's even harder. Way, way, way harder. Alright, so let's compare our ionization energies. Remember, the closer you get up here, the more energy it's going to take. So aluminum and sulfur. Sulfur is closest to that corner, so it's going to have the greater ionization energy. As, arsenic, and antimony. Arsenic is closer to that corner, so it's going to be a higher energy. And nitrogen and silicon. Once again, nitrogen is closer. And that's how you compare and predict the ionization energy comparisons.